Hello my friends and welcome back to the Today Machine channel, Surveying and Marking. The operation begins with surveying the site based on approved architectural and engineering drawings, drilling the hole. Using an auger or bored pile drilling machine, an initial hole is drilled to a depth of 20 to 30 meters, depending on design requirements. A temporary steel casing, typically 16 meters deep, is inserted into the hole to maintain vertical alignment. The casing is installed using a vibrating hammer, with its vertical accuracy checked using a plumb line. Once the temporary casing is in place, further drilling continues to reach the design depth, penetrating hard soil or bedrock layers. This ensures the pile acts either as a friction pile or an end-bearing pile. Use of polymeric slurry. Polymeric slurry is pumped into the drilled hole to stabilize the walls and prevent soil collapse. The slurry also helps balance the pressure against surrounding soil during drilling. This material is preferred over traditional bentonite slurry due to its suitability for smaller construction sites, ease of disposal, and cost efficiency. Excess slurry is recycled for subsequent drilling. The bored pile technique is a vital foundation method for large structures, particularly in challenging soil conditions where stability is critical. It involves the creation of deep, load-bearing concrete piles cast in situ. Insertion of reinforcement cage. After achieving the desired depth, a prefabricated steel reinforcement cage is lowered into the hole. The cage is precisely positioned and welded to the steel casing for stability. This structure provides the pile with its necessary load-bearing capacity. Finishing steps. After pouring, the temporary steel casing is removed. The slurry displaced by the concrete is collected for disposal or recycling. Once the concrete sets, any excess reinforcement bars above the ground level are trimmed. The bored pile is left to cure before further construction. Types of bored pile walls. There are three common configurations of bored pile walls. Contiguous walls. Bored piles are spaced closely, leaving small gaps filled with concrete to support the structure. Concrete pouring via tremie tube. A tremie tube is inserted section by section into the hole. Concrete is poured from the bottom up through the tube, ensuring uniform compaction and displacing the polymeric slurry upwards. The tremie tube is gradually removed during this process, cleaned with water, and reused. For the project at Desa Sri Hartamas in Kuala Lumpur, contiguous bored pile walls are employed. The gaps between piles are sealed with mortar to enhance groundwater resistance and stabilize the excavation site. Interlocking walls. Piles interlock to create a continuous wall, providing superior soil retention and groundwater control. Secant walls. Alternate hard and soft piles interlock, offering high stiffness and sealing. Advantages. Bored piles offer significant advantages over other piling methods, including reduced noise, minimal vibration, and the ability to adapt to variable soil conditions. They are particularly economical for deep foundations in dense urban areas or sites with complex geotechnical challenges. A concrete mixer with pump machine is an innovative piece of construction equipment that integrates mixing and pumping functions, making it highly efficient for various construction projects. Key components and functionality. Raw material feeding. The process begins with the feeding of raw materials into the mixing drum. This is typically done through a hopper, where cement, sand, gravel, and water are loaded in specific proportions. Some machines include an automatic batching system for precise measurements. Mixing mechanism. Inside the drum, rotating blades or paddles mix the materials thoroughly to achieve a consistent concrete mix. The mixing time is controlled to ensure uniformity. Advanced models may have a reversing drum mechanism for improved mixing efficiency. Pumping system. After mixing, the concrete is transferred to the pumping system. This section consists of a hydraulic pump, S-valve, or piston mechanism that pushes the concrete through a delivery pipeline. The hydraulic system ensures smooth and continuous pumping, even for high-viscosity concrete. Delivery pipeline. The mixed concrete flows through flexible or rigid pipes connected to the pump. Depending on the model, these pipelines can extend to significant lengths and heights, making it ideal for high-rise construction or hard-to-reach areas. Control system. Modern concrete mixer pump machines are equipped with user-friendly control panels. Operators can adjust the mixing speed, pumping pressure, and delivery flow as per project requirements. Mobility. Mounted on a mobile trailer, the machine can be easily transported to various sites. Its compact design makes it suitable for narrow spaces and urban construction areas. By combining the functions of a concrete mixer and a pump, this machine minimizes manual labor, reduces material wastage, and enhances project efficiency, making it a valuable asset in the construction industry. The system is designed to mix raw materials, such as cement, sand, and aggregate, into concrete and then pump the mixed concrete to the desired location. It's especially useful for projects in remote areas or those with limited access for traditional concrete delivery methods. Construction of high-rise apartment buildings in the U.S. Core rebar and post-tension slabs. The construction of high-rise apartment buildings in the United States involves advanced engineering, efficient methods, and rigorous safety standards. Typically ranging from 20 to over 50 stories, these structures use a combination of reinforced concrete cores and post-tension slabs to ensure stability, durability, and efficiency. Concrete core and reinforcement. The building's structural core, often called the spine, houses elevators, stairwells, and mechanical shafts. It provides lateral stability against wind and seismic forces. The core walls, typically 18 to 24 inches thick, are heavily reinforced with rebar. For a 50-story building, the steel reinforcement can weigh up to 3,000 tons, depending on seismic and wind load requirements. Rebar grids are placed at 12-inch spacing for enhanced strength. Modern projects often use self-climbing formwork systems, which move upwards with each level, saving weeks of labor. Post-tension slabs. Floors are constructed using post-tensioned concrete slabs, ideal for high-rise buildings due to their lightweight and flexibility. Post-tensioning involves placing steel tendons, cables, within the slab, which are tensioned after the concrete sets. This method allows for thinner slabs, typically 7 to 12 inches thick, reducing material use and overall weight. A single floor of a high-rise can be completed in 4 to 7 days using this method, streamlining construction timelines. Key metrics and speed. High-rise buildings often use tower cranes capable of lifting up to 40,000 pounds to manage heavy loads like rebar and concrete buckets. A 50-story building can require 75,000 cubic yards of concrete, equating to approximately 7,500 truckloads. Advanced techniques and prefabricated components allow completion of a typical high-rise in 2 to 3 years, with the core construction often taking 12 to 18 months. Sustainability. Many high-rise projects now use sustainable practices, such as recycled steel for rebar and concrete mixes incorporating fly ash or slag. This reduces the environmental impact while meeting structural requirements. Efficient methods like post-tension slabs and reinforced cores make modern high-rises safer, faster to build, and more cost-effective, addressing the growing demand for urban living spaces in the U.S. The field fillet-welded moment frame connection process is a multi-step procedure that ensures structural integrity and efficiency in steel construction. Column installation. The process begins with the installation of moment frame columns. Columns, often prefabricated with side plates and top deck angles attached, are lifted and positioned using industry-standard lifting techniques such as lifting lugs or chokers. Attention is given to column splices and anchor bolts to ensure proper alignment and elevation. Columns may accommodate 1 or 2 beams, forming one-sided or two-sided connections. Beam installation. Beams are installed between the side plates using vertical angles, top cover plates, and bottom cover plates. The top cover plate is slightly narrower than the column flange for ease of fitting, while the bottom cover plate is wider. Temporary construction aids ensure smooth installation. Once beams are positioned, initial bolts are installed to secure them before releasing the crane. Bolt installation and tightening. All required bolts are inserted through slotted or oversized holes, depending on project specifics. These bolts act as clamps to close any root gaps between components. Temporary construction aids are carefully removed, and the bolts are tightened to ensure structural fit. Fillet welding and final steps. Horizontal fillet welds join the side plates to the cover plates, while vertical welds secure the side plates to the vertical angles. Once the welding is complete, fireproofing materials, such as sprayed fire-resistant coatings or metal strips, are applied to ensure safety. The process concludes with the marking of protected zones, ensuring compliance with safety standards and readiness for further construction stages. High-rise concrete pours in Seattle are a remarkable display of precision, teamwork, and endurance. As the city's skyline continues to rise, local 528 cement masons play a pivotal role in shaping its future. The process of pouring concrete for a high-rise building is both an art and a science, demanding skill, coordination, and stamina. On poor day, the crew assembles early, preparing for a task that spans hours of rigorous labor. For a project like a 20-floor high-rise, the pour involves covering approximately 10,000 square feet of deck space with fresh concrete. The process begins with the arrival of concrete, transported via pump trucks that deliver the material to the designated floor. Using advanced pumping systems, the concrete is methodically spread across the deck. Cement masons ensure even distribution and proper compaction to eliminate air pockets, which could compromise the structural integrity. Throughout the pour, the crew works efficiently, utilizing tools like screeds and bull floats to achieve a smooth, level finish. The cement masons continuously monitor the material's consistency and ensure the concrete adheres to stringent specifications. Every movement is purposeful, as timing is critical. The concrete must be worked before it begins to set. After roughly 4 hours, the freshly poured concrete becomes firm enough to walk on, marking a milestone in the day's progress. This allows the crew to commence additional finishing tasks, such as edging and joint cutting, to prevent cracks and ensure durability. Safety is paramount during high-rise pours. Cement masons and laborers adhere to rigorous safety protocols, including wearing protective gear and maintaining clear communication to avoid hazards in the bustling work environment. Once the concrete sets sufficiently, the team transitions to cleanup, meticulously removing equipment and preparing the site for the next phase of construction. The crew's dedication ensures that each pour lays the foundation for a solid and enduring structure. High-rise concrete pours are a testament to human ingenuity and resilience. From start to finish, the process reflects the expertise and determination of those who contribute to Seattle's ever-evolving skyline. For local 528 cement masons, every pour is not just another day at work, it's a step toward building a city that reaches for the skies. The fly ash brick making machine with a 12-cavity automatic mold operates by mixing fly ash, cement, sand, and water in precise proportions. The mixture is fed into the mold cavities, where hydraulic pressure compresses it into uniform bricks. The automated system ensures high-speed production, with efficient curing and stacking, achieving a capacity of 16,000 bricks per shift. Concrete bricks offer several advantages over traditional clay bricks. First, they are more environmentally friendly, as they reduce the need for natural clay resources and minimize emissions during production. Second, concrete bricks have higher strength and durability, making them suitable for heavy-duty applications and ensuring a longer lifespan. They also provide better thermal and sound insulation, enhancing energy efficiency and comfort in buildings. Additionally, their uniform size and shape facilitate easier and faster construction, saving time and labor costs. Concrete bricks can also be produced in various colors and finishes, offering more design flexibility. Overall, they are a cost-effective and sustainable alternative for modern construction needs. The semi-automatic method for laying aerated and foam concrete blocks is a modern, efficient solution that simplifies and accelerates construction processes. This method utilizes a specially designed semi-automatic device, which ensures precise placement of blocks while minimizing labor efforts. The device typically consists of a guided frame or rails that align blocks accurately during installation. With a built-in mechanism for applying adhesive or mortar, the system ensures uniform distribution, enhancing the strength and thermal insulation of the structure. Operators place the blocks in the designated slots, and the device automatically adjusts their positioning to create tight, consistent joints. This method significantly reduces manual work, increases productivity, and ensures high precision in block alignment. It also minimizes the use of adhesive materials, making it cost-effective and environmentally friendly. The semi-automatic system is particularly useful for constructing walls in residential, commercial, and industrial buildings. The Hume Dam upgrade focused on constructing a 50,000-ton mass concrete buttress along the southern training wall. This major infrastructure enhancement aimed to bolster the embankment's structural integrity, enabling it to withstand extreme seismic events. Funded collaboratively by the Australian, New South Wales, Victorian, and South Australian governments through the Murray-Darling Basin Authority, the project addressed critical safety and sustainability concerns for the dam. The mass concrete buttress, strategically positioned in the river and against the southern training wall, provides essential support to the embankment. By redistributing forces and stabilizing the structure, the buttress ensures long-term resilience in the face of potential earthquakes. McConnell Dowell Constructors, a renowned contractor, executed the construction, while the State Water Corporation managed the project with detailed designs by Erques Australia. The upgrade involved meticulous planning and execution. A time-lapse video captured by 2 cameras documented the transformation, showcasing the scale and precision of the work. Each phase, from material preparation to final placement, demonstrated the coordination required to achieve this engineering feat. The project concluded successfully in November many years ago, with a total cost of approximately $30 million. This upgrade represents a significant advancement in dam engineering, ensuring that the Hume Dam continues to serve as a vital water management resource in the Murray-Darling Basin while prioritizing public safety and infrastructure resilience. The construction of the bridge over the Erques ravine in Tenerife, Canary Islands, showcases a well-coordinated process. The assembly involved multiple stages, each leveraging advanced engineering techniques and heavy machinery. The project began with the preparation of the worksite and the assembly of the first arch, supported by a 400-ton crane and a 200-ton crane. The arch, with a total length of 116 meters, was lifted and secured in place with precision. Following this, the second arch, measuring 110 meters, was assembled in a similar manner using the same crane configuration. These stages required seamless synchronization to ensure stability and alignment of the structural components. To enhance the durability and load-bearing capacity, expansion concrete was poured into the first arch after its assembly. This process was repeated for the second arch, creating a robust foundation for the subsequent phases of construction. The next phase involved the placement of floor beams to form the spans. The second span comprised beams weighing 32.5 tons, carefully positioned using heavy cranes, including an LR1600 and a 220-ton crane. Similarly, the beams for the first span were installed with the same precision, ensuring the structural integrity of the bridge deck. The Sound Transit South 200th Link Extension expands Seattle's light rail system by 1.6 miles, 2.6 kilometers, from SeaTac Airport to South 200th Street and 28th Avenue South. This project features an elevated guideway with precast segmental construction, including twin and single-track box girders. Typical spans, up to 130 feet 6 in, 39.8 meters, are simply supported, while continuous structures are used for longer spans up to 156 feet, 47.5 meters. Two significant bridges near SeaTac Airport include main spans of 333 feet, 101.5 meters, and 363 feet, 110.6 meters. Typical spans are installed using overhead trusses, while long spans are built in balanced cantilever with cranes, ensuring precise and efficient construction. The construction of a steel girder bridge typically involves several coordinated phases to ensure structural integrity and long-term performance. Below is a detailed breakdown of the process. Erection of steel girders. The process begins with the fabrication of steel girders in a controlled facility. These girders, often fabricated from ASTM A992 steel with a typical yield strength of 50 ksi, 345 megapascals, are delivered to the site. Using heavy-duty cranes with lifting capacities of up to 500 tons, the girders are precisely positioned onto pre-installed reinforced concrete abutments and piers. Anchor bolts with diameters ranging from 1 to 2 inches, 25 to 50 millimeters, are employed to secure the girders. Installation of steel bar girders. Once the main girders are in place, steel bar girders, also known as rebar cages, are woven atop the primary structure to reinforce the concrete deck. These rebar cages are constructed from grade 60 reinforcement bars with a tensile strength of 60 ksi, 414 megapascals. Bar diameters typically range from #4, 0.5 inches or 12.7 millimeters, to number 11, 1.41 inches or 35.8 millimeters, depending on load requirements. The spacing of bars is calculated based on design load specifications, with common intervals of 6 to 12 inches, 150 to 300 millimeters, to achieve optimal reinforcement. Concrete pouring and deck formation. Concrete, typically a high-performance mix with a compressive strength of 4,000 to 6,000 psi, 28 to 41 megapascals, is poured over the steel bar girders. To ensure proper curing, the concrete is poured in sections, using formwork to support its weight during hardening. The entire deck is compacted and leveled using vibratory equipment to eliminate voids and improve strength. The curing process spans 7 to 28 days, depending on the environmental conditions and mix design. Upon completion, the bridge is inspected for structural compliance and tested for load-bearing capacity, ensuring a durable and safe structure. The installation of hybrid grass at the Atatürk Olympic Stadium, Istanbul, Turkey, was planned and executed to meet UEFA's rigorous standards for the 2020 Champions League final. The process began with the removal of the existing turf, followed by the extraction of the old root zone layer to ensure a solid foundation for the new system. Next, a new root zone layer was established, carefully leveled and compacted to create an even surface. This precision step was crucial for the stability and performance of the hybrid grass. Rolls of hybrid grass were then unrolled across the prepared surface, with edge trimming performed to ensure a seamless fit. The edges of the rolls were securely seamed to eliminate gaps and enhance durability. Following this, the root zone was infilled with a specific mixture to promote growth and provide optimal support for the grass blades. The surface was then brushed to evenly distribute the infill material and ensure a smooth finish. The final step involved seeding the hybrid grass system to allow natural grass to grow and integrate with the synthetic fibers, creating a resilient and visually appealing pitch. This comprehensive process culminated in a world-class playing surface. The pitch received many 5-star rating from UEFA consultants. The brick pressure cleaning process begins with an assessment of the surface to determine the appropriate cleaning method and pressure level. A pre-treatment solution is applied to loosen dirt, grime, mold, and stains without damaging the brick or mortar. High-pressure water is then used to thoroughly clean the surface, targeting deep-seated debris and discoloration. For tougher stains, additional cleaning agents may be used. Once cleaned, the surface is rinsed to remove any residue, leaving the bricks looking refreshed. Optional sealing can be applied to protect the bricks from future staining and weathering, ensuring long-lasting results and improved curb appeal. The industrial lifting production industry is a cornerstone of global infrastructure and manufacturing, supporting diverse sectors like construction, shipping, energy, and aerospace. This industry specializes in creating and testing lifting solutions that ensure the safe and efficient handling of heavy loads. Key offerings include wire rope slings, synthetic slings, rigging rentals, proof load testing, and advanced fabrication services. Wire rope slings. Wire rope slings are one of the most widely used lifting tools in the industry. Constructed from high-tensile steel wires, these slings are designed for strength, flexibility, and durability. They can handle load capacities ranging from 1 ton to 500 tons, depending on the rope diameter and construction. Wire rope slings are essential for heavy lifting in industries such as shipbuilding, offshore drilling, and steel manufacturing. Moorebar rigging rentals. Rigging rentals are a cost-effective solution for projects requiring temporary lifting equipment. Companies like Moorebar Rigging Rentals provide access to a vast inventory of lifting tools, including shackles, chain hoists, turnbuckles, and spreader beams. Rentals allow companies to optimize their operations without the need for significant capital investment. Water bag proof load testing. Water bag proof load testing is an innovative and environmentally friendly method used to certify the load capacity of lifting equipment. These water-filled bags simulate real-world loads and can test equipment with capacities ranging from 1 ton to over 100 tons. This method is ideal for testing cranes, hoists, and davits, ensuring they meet safety and operational standards. Synthetic slings. Synthetic slings, made from materials like polyester and nylon, offer lightweight and flexible alternatives to traditional wire rope and chain slings. Despite their reduced weight, they provide impressive load-bearing capacities, with some slings capable of handling loads up to 200 tons. These slings are particularly suited for lifting delicate or irregularly shaped objects, as their soft texture reduces the risk of damage. Testing services. The industry places a premium on safety, and rigorous testing services are integral to maintaining high standards. Advanced test beds with capacities up to 5,000 tons are used to simulate real-world conditions and certify the performance of lifting equipment. These test beds ensure compliance with international standards such as ISO, ASME, and API. (3,000-ton and 5,000-ton test beds). Test beds with capacities of 3,000 tons and 5,000 tons represent the cutting edge in lifting equipment certification. These facilities test the braking strength, elongation, and resilience of wire ropes, slings, and chains under extreme loads. By replicating demanding operating conditions, these test beds ensure the reliability of equipment used in critical applications such as offshore oil platforms and aerospace projects. Chain and fiber rope division. Chains and fiber ropes are essential components in lifting and rigging operations. High-grade alloy chains are favored for their strength and durability, with capacities ranging from 2 tons to 500 tons. Fiber ropes, on the other hand, are lightweight and highly flexible, making them ideal for maritime and rescue applications. Modern fiber ropes, made from advanced materials like Dyneema, can match or even surpass the strength of steel while being significantly lighter. Fabrication services. Custom fabrication services are another vital aspect of the industrial lifting industry. These services include the design and manufacturing of bespoke lifting solutions such as lifting beams, spreader bars, and custom rigging hardware. Modern fabrication facilities leverage CNC machining, robotic welding, and 3D modeling to produce equipment tailored to specific client needs. The SOM Splice 6000 kN hydraulic swagger is designed for precise and reliable swagging of wire rope slings up to 38 mm (1.5) in diameter. Operated via a single-column hydraulic system, the machine generates 6,000 kilonewtons (612 metric tons) of force to uniformly compress and form wire rope terminations. The swagging process begins with placing the wire rope and fitting into the die set. Activating the hydraulic system initiates a controlled compression cycle, ensuring consistent and secure fittings. Built to ISO 9001-2000 standards, it adheres to N693 and N982 for safety and performance, offering robust and user-friendly operation. The metal scrap and cars shredder efficiently cut and process light to medium-sized scrap metal. Their compact size and lightweight design allow for easy transportation using a truck with a roll-on/off system. The shredder are versatile, operating with either a diesel or electric engine, and can function on various terrains, making them adaptable to diverse environments. Equipped with a robust cutting mechanism, these shears deliver precise and consistent results while minimizing operating costs. Their user-friendly design ensures straightforward operation and maintenance, enabling quick deployment and reducing downtime. The process of remelting and recycling aluminum is a cornerstone of sustainable practices in the aluminum industry, offering significant environmental and economic benefits. Recycling aluminum requires only about 5% of the energy needed to produce primary aluminum, drastically reducing carbon emissions. This energy efficiency makes the circular economy an essential focus for the industry. Modern remelting facilities integrate advanced technologies to optimize the use of scrap aluminum. For example, systems like batch intelligence enable precise sorting, storage, and integration of recycled aluminum into production batches, ensuring high-quality output while maximizing the use of secondary materials. These systems calculate optimal batch compositions and employ automated transport and storage solutions to enhance efficiency and safety. The quality of the recycled aluminum depends heavily on the quality and sorting of the scrap. Automated systems ensure that materials are processed under strict safety protocols, with mechanisms like light barriers to protect workers from potential hazards. Additionally, improved logistics and automation reduce human intervention in high-risk areas, enhancing workplace safety. By increasing the use of recycled materials, the reliance on primary aluminum is minimized, leading to a reduced carbon footprint for aluminum products. Investments in such innovative technologies underscore a commitment to sustainability, efficiency, and safety in aluminum production. Raw material. The process begins with high-quality, validated flat steel known for its excellent wear resistance and hardness properties. 6-meter-long steel bars are cut into sections approximately 300 millimeters in length. Forging phase. The cut steel pieces are heated in a rotary furnace to about 1,200 degrees Celsius, glowing bright as they reach forging temperature. The heated sections then go through several steps in a forging press. First, the raw material is formed into its base shape. Next, the eye of the hoe is created, followed by the shaping of the wide blade and the punching of the final raw part. Shaping the final form. Subsequent press operations create the characteristic 90-degree offset between the two hoe blades. The blades are then forged to achieve the desired thickness and strength. A contour cutting process gives the hoe its final, distinctive shape. The production of the Hoopoe hoe, a specialized forestry tool used for planting seedlings during reforestation, involves several precise steps. The hoe gets its name from its 90-degree rotated double blade, which resembles the head of a hoopoe bird. Hardening process. Since the blade edges remain soft at this stage, they undergo a hardening process. Due to varying material thicknesses, only 1/3 of the blades are selectively heated and then quenched in water. This method prevents internal stresses or deformations that could occur during full quenching. Grinding and finishing. After hardening, the blade edges are ground using wet grindstones to avoid overheating, which could compromise the hardness of the cutting edges. The hoes are then coated in a painting facility, where they are primed, painted, and dried to ensure durability and protection against environmental factors. Assembly and final inspection. In the final stage, an ergonomic handle made from sustainably sourced ash wood is attached. Ash wood is ideal for hand tools due to its high strength, hardness, and flexibility. Additional fastening with clamps or nails is unnecessary, as the assembly ensures a secure fit.